Hello everyone, my name is Zach, and last time we talked about the basic ins and outs of yo-yo design, and how to design the guts of your yo-yo. We ended with me leaving out how to design for your axle, leaving the pre-stated 3-part checklist of the video unsatisfactorily incomplete. So let's go back and look again at what we want to do in our design. We want to design a yo-yo for 1A that weighs 65 grams, has an outer diameter of 54 millimeters, and a width of 45 millimeters. And we also know it will have a C-sized bearing and standard 19 millimeter response. But two things that were left relatively ambiguous in our design were the gap and anything having to do with the axle. The reason for this is that these two pieces of information are dependent upon the actual geometry of your design, meaning that sketch I was putting off doing for the majority of the last video. Side note, just as a general rule of thumb, a lot of yo-yo axles are M4 by 0.7 metric set screws with either oval heads or flat heads, and the average of all the clients that I have designed for is either an 8mm long axle or a 10mm long axle. So if you don't want to pay attention to anything else in this video, there you go. Back on topic now. It's finally time to sketch our yo-yo quarter section in the box. But in order to do that, we must talk about what I will call the fundamental design philosophy. The fundamental design philosophy is that, in general, the profile is for comfort and some optimal type of play, and the cup is for performance and weight distribution. However, some profiles, cups, and combinations of the two can either accentuate or disqualify certain performance attributes. Before we sketch anything, just because we think it's going to look cool, let's document and clarify what exactly I want my yo-yo to let me do with it. Let's define our design criteria. 1. I want my yo-yo to be able to handle my speedy tricks without instability or snagging. 2. I want my yo-yo to be able to sleep for a satisfactory amount of time, as I don't tend to regen my yo-yo as much as I just throw it hard then do a long combo. 3. I want my yo-yo to be able to grind well both with thumb grinds and with inner rim grinds. 4. I want my yo-yo to have a smooth profile with an organic shape, but I also want it to feel like an H-shape yo-yo as well. 5. I want my yo-yo to be comfy in the hand, and I am willing to sacrifice ease of landing it on the string in order to obtain this. To an experienced designer, these 5 bullet points are 80% of the design. Each one contains an incredible amount of information, so let's translate exactly what they mean to the design. For the purposes of my sanity, and with respect for the several weeks I've been trying to animate this by hand, we're now going to jump into my computer-assisted design software, Solidworks 2015. I'll talk about CAD software in a later video if you all would like me to, but most half-decent CAD software can be used to design yo-yos. Number 1. I want my yo-yo to be able to handle my speedy tricks without instability. In order to design for these traits, you need to keep in mind what causes the two negative traits you're trying to avoid: instability and snagging. Instability can be caused in 2 frequently occurring ways, the first and most common of which is a lack of rim weight. You can learn more about this in the first extra lesson video. And the second of which actually has to do with wall height. Essentially, when you're doing tricks and the direction of the string the yo-yo is resting on stops being coplanar with the plane normal to the axis of rotation, the result is a net torque on the yo-yo which is shifted 90 degrees due to a combination of gyroscopics and the right-hand rule, causing the yo-yo to tilt and fall over. In simpler terms, high walls means more leverage from the force from the strings, means more tilt, means less stability. Now, having low walls can have negative side effects in some very, very specific cases, but I'll get to that later if I must. Long story short, take away from this first specification that because you want stability, you want a low wall and a respectable amount of rim weight. Number 2. I want my yo-yo to be able to sleep for a satisfactory amount of time, as I don't tend to regen my yo-yo as much as I just throw it hard then do a long combo. This essentially means that, just as was discerned from the first bullet point, a considerable amount of rim weight is requested. Number 3. I want my yo-yo to be able to grind well both with thumb grinds and with inner rim grinds. Aha! Now this is a very specific requirement. The thumb grind requirement essentially means that minimizing surface area in the profile is a good design choice, and because circles have the lowest perimeter per unit of enclosed area, it is a good decision to draw the profile with either a small amount of smooth curves or an even smaller amount of straight lines with curves between them. Additionally, the inner rim grind requirement refers to the area near the outside of the cup of the yo-yo where a finger or thumb ought be able to catch the yo-yo there for a grind, requiring a straight line at least parallel to the axis of rotation or steeper, but not too steep. How steep is too steep? I'll talk about that in a later video on limit state design and machinability. Number 4. I want my yo-yo to have a smooth profile with an organic shape, but I also want it to feel a little bit like an H-shape yo-yo as well. Simply speaking, this is very straightforward. Given that the only way for an H-shaped yo-yo to look like an H-shaped yo-yo is for it to have the outermost parts of the profile start steep and then get flatter, that is what we know it must look like. And because we know from requirement number 3 that this must be conductive to thumb grinds, that it must be organic at the bottom in order to make room for the grinding finger, and there we have it. Number 5. I want it to be comfy in the hand, and I am willing to sacrifice ease of landing it on the string in order to obtain this. This is the final piece of the puzzle for the profile. Comfort in the hand is a very subjective topic, as it varies a lot based upon personal preference as well as size of the hand of the thrower. A few general design criteria do exist, however. A comfy throw has a larger area to disperse the impact force when it returns to your hand, and the rim shouldn't be too sharp. That means that you must take the outermost point of the yo-yo's radius and move it further away from the outermost point of the yo-yo's width, thus shrinking what is known as the effective catch zone, in order to subsequently increase the edge radius. Without any new numbers or data, we're already this far. It's time to fill in the rest of the sketch by answering in more detail what the first 2 questions we had going into this video were. What about the gap? And what about the axle? Consulting the graph on bind difficulty from lesson 1, we can recall that this yo-yo has more rim weight and will therefore spin slower, and therefore needs a relatively small gap. But we also have a counteracting design criteria wherein the design requirements specified that I don't tend to regen my yo-yo too much, meaning that it doesn't need to be as snappy of a response as it would have been otherwise. And because this yo-yo is going to be one used for speedy tricks, as was specified in design requirement number 1, widening the gap slightly still holds as a wise design choice. In the first video, I stated that I designed my gaps by dimensioning an offset off the top of the pad from the bottom of the bearing, and that my default dimension was going to be 0.2 millimeters offset, yielding a gap of 4.3625 millimeters. So I will widen the gap by shrinking the offset down to 0.17 millimeters, making the gap 4.4225 millimeters. That's the gap. Now on to the axle. The reason I have not filled in this gaping hole in the cup of the yo-yo is that I cannot do that until I know exactly how long my axle is going to be. If you want to take your already high rim weight and make it even higher, you can design your yo-yo to have a shorter axle, as I explained in the first extra lesson video. However, do keep in mind that with shorter axles come lower durability, as aluminum is already a very weak metal. Threads are usually very easily damageable by impact forces like those from drops or dings, and being perfectly honest with you all, I don't like treating my yo-yos like they're made of fine china, so I'm going to bite the relatively low caliber bullet on performance and put my axle length at a little bit longer than the average M4 axle length at 10 millimeters long. So now, in order to drill my hole the right depth, I'm going to need to activate my algebra powers. We need to remember that the line of symmetry is offset from the end of the mounting shaft by exactly half of the width of my bearing, which is 1/2 of 3/16 of an inch. And given that I want my axle to be in the dead center of my yo-yo, I will simply measure half the length of the axle away from this line of symmetry, subtract half the width, and then that's the depth of my hole, right? No. You forgot something important. Because aluminum is flexible, as you tighten the yo-yo halves together, the axle would have no wiggle room and you would be stressing the threads without actually tightening the yo-yo. To compensate for this, you just need to drill your hole a little bit deeper. How much deeper? Well, that depends on the type of axles you're using, or rather, what type of thread you are cutting into your hole for your axle to thread into. For all practical intents and purposes, threads are really complicated. If you hate me enough to make me explain it fully, ask me so in the comments. There are 3 pieces of information needed to thread the hole for your axle. The measurement system, ISO versus ANSI, where if it's metric, you use ISO, and if it's imperial or in the United States, you use ANSI. The machine screw diameter, or thread size, which is basically almost the average diameter of your threaded thingy you're threading into the threaded hole. And finally, the pitch of your thread, which is how far forward my threaded thingy would move if I rotated it 360 degrees. I have found that making your threaded hole deeper by approximately 0.75% of the pitch works quite nicely, because that means that the thrower would need to over-tighten their yo-yo by 1.5 full turns in order to make the axle run into the bottom of both holes. And at that point, it would be a good bet that the threads would have stripped by then, regardless of what axle or even metal you're using. So, given that my axle is an M4 by 0.7 ISO metric thread, where that second number has secretly been the pitch this whole time, I take 0.7 millimeters, multiply it by 0.75, get 0.525 millimeters, say, yeah, whatever, that's close enough to 0.5 millimeters, and then add 0.5 millimeters to the depth of the hole, and there we have it. Now that we finally know how deep our axle hole is going to be, oh, wait, we don't know that yet? Yep, we don't. I told you threads were complicated, because your machinist will know this, hopefully, but you, in the meantime, do not. You see, drilled holes don't look like cylinders. They look like slightly mean and pointy cylinders, because that's what drills look like. Meaning, we may only be able to push a cylinder down a hole this far, but if we want that cylinder to go down that far, that means our hole is going to have a cone of nothingness that goes a little bit further. How much further? Well, you can figure that out by drawing an isosceles triangle with an obtuse angle of 118 degrees, cutting the triangle in half with a line following the axis of rotation of the yo-yo, resulting in a right triangle of half that original angle, which is 59 degrees, and half that original base length, which was something called the, quote, maximum minor diameter, end quote, which, for an M4 by 0.7 thread, according to the modern-day divination tablet that is known as the metric tap and thread chart, about 3.3 millimeters. So that divided by 2 is 1.65 millimeters. Then, using some basic trigonometry, we know that the tangent of 59 degrees is equal to 1.65 millimeters divided by our unknown additional hole depth, and by solving for the unknown, we find that it is deeper by 0.9914 millimeters. So now, we finally know how deep our axle hole is going to be, so we can finally start designing our cup. As a general rule of thumb, people who don't want that whole exposed axle look, which is most people, should leave at least 0.5 millimeters of aluminum around the axle hole to make sure that there's no chance of the axle accidentally breaking through if someone tried to twist their axle in too far. So now I know that in order to keep my original criteria of far more rim weight, I may need to balance out a few things. I know with certainty that the more of the yo-yo I put towards the axle, the worse it's going to be for the rim weight. So I'm going to try and put as little material there as possible, not worrying about the looks as much because I don't very much care about what the yo-yo looks like. I do, however, know that I want the cup area around the axle to be relatively flat, and I want it to be relatively curvy as it comes off the flat parts. Cutting to the chase, how much material do I need to put there? How thin can I make it, and how much material can I just cut away and shove to the rims for more rim weight? The answer to this question depends on a lot of stuff, and I will talk about this more at length in my next video. But for now, I will simply say that for 6061 yo-yos with diameters between 50 millimeters and 60 millimeters and widths between 39 millimeters and 47 millimeters, a minimum thickness of 1.5 millimeters will assure relatively dependable structural integrity. But you are able to go thinner a lot of the time and still not run into any problems. With that said, now that I know how thin the cup can be, I will just fill in around what's there in a way I think will look pretty, and then I will measure everywhere along the yo-yo to make sure no part of it is thinner than 1.5 millimeters, and there we have it.
Congratulations!
You are officially 90% done with the yo-yo design. Now, all that you have to do is come to the realization that you're actually really far away from done. You know, everything about this yo-yo should be fitting into your design criteria. However, once you actually put this yo-yo into 3D, make its density that of 6061 aluminum, put in a bearing that weighs as much as bearings and pads and the axle, and check on how heavy it is, you realize that you've completely missed your target. Okay, so now all that you have to do is just tweak stuff around, drag a few points to add or take off some mass here and there, and then after just a little bit of teasing and poking and prodding, your yo-yo is now at just the right mass. Awesome. But now that you've done all that, what did you do to the rim weightedness? Odds are you've changed that too. And that is the difficult heart of the matter. You cannot change the mass and expect the weight distribution to stay the same. And the only way to get good at changing one without changing the other, unless you are very, very proficient at CAD software, is to go slow, to check your values frequently, and to practice. And without further delay, there we have it. We have successfully designed a yo-yo whose performance we more or less have predicted. The next video in this series will be about jumping into the shoes of the machinist, whom you asked to manufacture this yo-yo for you, and discussing how manufacturing friendly your design actually is, as well as how structurally robust it actually is. The next video will be on limit state design and design for manufacturing. Thanks for watching.